Nice. Okay. Good afternoon, everyone. I'm Amin, a recent master graduate from Politecnico di Milano, and I am going to present our paper, a monitoring-oriented digital twin pipeline for data-driven prediction of residential prosumer energy profile. So the idea of the work is simple. We take a real monitor residential building and transform its operational data into a traceable prediction pipeline. The focus is not only on the prediction traceability, it's also on how the data are prepared and how the missing values are handled, and finally how the result actually support monitoring. So, as you know, the residential prosumer building are very difficult to predict because they are not follow a clear usage pattern, unlike, for example, commercial buildings or other buildings with a specific function. In our case study, different drivers interact, for example, PV generations, pool circuit, hybrid HVAC system, and finally our IoT telemetry streams contains a lot of gaps and outages. And our observed whole building demand our observed whole building demands shaped based on the user pattern, in user behavior, physical system, and also imperfect monitoring. So monitoring needs an expected feature reference, so we cannot just rely on the raw demand streams thresholds. The case study on this paper is the strength point of it, because it's not just a generic data set, it is a real monitored villa in Segrate near Milano. It is over 30 years old. It is quite big across 3 levels. It has PV array, outdoor swimming pool, hybrid heating system with the heat pump, gas boiler, mechanical ventilation with the heat recovery, and so on. So before we going further, I want to clarify what does digital twin means in this project. The digital twin in this project does not mean a fully visual replica of the building or a closed-loop control system. It is an operational phase analytics layer. Basically, it's going to link the physical building to a digital representation based on early signals, monitoring boundary, and provenances. And finally, our analytics layer going to produce us the baseline predictions and residual, which with these outputs, we can actually going to compare the actual and expected demand of the building and help us in the anomaly detection. So to keep the digital twin traceable, we just choose 4 main core streams, which they are whole building demand, PV generation, pool circuit, and the outdoor temperature. This was intentional design choice, except going to choose every available sensor at the building. This is actually makes our case study interesting because several source streams of operational complexity are present in just one building, like on-site generation, high load switching, seasonal HVAC operation. Of course, our actually streams contains a lot of missing values and outages. Also, this case study allows us to test our pipeline under realistic residential conditions. So, as I mentioned before, our case study, specifically this villa, contains a lot of missing values. So it's not a very complete, perfect data streams. You can see the numbers of missing values for each sensor that we had. At the downside of the slide, you can see also we used billing comparison and monthly coverage as a data quality check to understand that our observed demand is reliable enough for scientific evaluation. So this slide shows a monitoring-oriented architecture. At the beginning, the heterogeneous IoTs aggregated through home assistant, and after that, the sensor identifier mapped to physical subsystem, and finally our analytics layer produced the predictions and residuals and comparing the expected and actual demand. Before we're going to create our data set design, we needed a traceable and clear hourly database. It started from a home assistant export from our four source of streams, and after that they are aligned to a common hourly grid, and after that cleaning rules and the missing flags are applied to them. And finally, our target shifted by 1 hour ahead and train test structure defined in a leakage-safe way. This step is very important because it's this is the backbone for our future dataset design. And this is not only going to make our prediction traceable, it is also is based on a controlled and traceable data engineering process. So based on our database, we created a controlled 2x2x2 dataset design. Maybe you ask yourself why this is like this 2x2x2 dataset design, because we had a lot of assumptions and we wanted to make sure which one of them going to get us the better result. Before I'm explaining, I want to tell you about the prediction contract. Our prediction contract here is 1 hour ahead demand baseline. What does it mean? It means that our model going to predict the demand at the time t plus 1, but by only the available information at the time t. So let's back to our dataset design. We had 3 experimental axes. The first one is imputation method, which gives us 2 pipeline A, pipeline B. Pipeline A actually using causal field, and it is our realistic deployment, while the pipeline B is uses interpolation, and it is our offline upper bound. The raw policy is the second one. What does it say? It says that we are going use the imputed raw, or just simply remove all the problematic raw data and use as a clean only. And the third one is the feature set. Feature set says that we are going only use the whole building demand, or we are going to include the subsystem telemetry to our whole building demand. So with these configurations, we can get this data set family. You can see here. These are 8 data set from A1 to B1. After analysis, we understand our main deployable data set is the A-tier configuration, which uses causal field and imputed raw, and include the subsystem telemetry to whole building demand. So all our models, such as persistent, multiple linear regression, and the random forest, evaluated under the same split and prediction contract. So the key result is that the A3 configuration improves the deployable baseline. You can see here the comparison between our 3 models. The random forest performs better, but the gain is not huge, but it is credible because it is obtained on the chronological, leakage-safe, and deployment-oriented process. Also, for this kind of the monitoring task, a moderate but defensible improvement is much useful than an optimistic but unrealistic data handling. So this slide says that the feature also is important for us, because the feature is not just make our prediction accurate, it's going to make it physically interpretable. For example, you can see here the most important feature group is pool circuit, and followed by the others. At the right side, you can see a comparison between the output of our random forest model with the actual demand. So to conclude, this paper contributes to a case study pipeline for realistic residential prosumer monitoring. So it started with the documenting a real villa testbed with the PV panel and so on, and after that provides a traceable pipeline based on the hourly UTC alignment, subsystem mapping, permanence, and leakage-safe evaluation. And finally, we figured out that the A3 configuration achieved the better result over the other dataset designs, and our random forest also performance better than persistent and multiple linear regression. So the next step is going to further to richer semantic integration, like IFC linked to subsystems and passive occupancy error and live deployment. The key, the main actually takeaway is that the imperfect residential telemetry still can become defensible residential reference as long as the pipeline is traceable and deployment aware. You can also find the process dataset and supporting code via this address. Thank you so much for your attention.